AI models are getting smaller, but somehow they're not getting weaker. For example, when GPT 5.4 mini was published, it was claimed to approach the performance of the larger GPT 5.4 model on several evaluations. Or recently, when Gemma 4 was released, it got a better score than some of the bigger models, even more than 3 times bigger than Gemma 4, which doesn't make sense and should not be possible, because for years the rule was simple. Bigger model means better AI. More parameters, more memory, more compute. That was the path forward, and it worked. Larger models wrote better text, generated better code, and handled more complex tasks. That is how we got models like GPT-4. But now something has changed. It looks like a kind of a new trend, that companies they try to publish mini versions beside the flagship LLMs. If smaller models are catching up, then size is no longer the full story. For a long time, scaling looked almost like magic. When you increase the size of a model and trained on more data, its performance improved across many tasks. That success shaped the entire industry. Companies invested billions of dollars into larger training runs, bigger clusters, and more powerful hardware. And to be fair, it worked. But bigger models came with real costs. They were slower, more expensive, and harder to deploy. And it's difficult to run them outside of large data centers. A smaller model today is not just a larger model with pieces removed. Increasingly, it's designed differently from the beginning. When people hear a small model, they often imagine something limited. But modern small models are becoming more specialized. They are more targeted and more efficient. Because of that, they can be surprisingly capable. They are not universally better than larger models, but they are often good enough for the job that you want them to do. And in the real-world systems, that is what matters. So how can a small model still feel powerful? The answer is not just one technique. The entire system around the model has improved. The data is better, the training is better, the architectures are more efficient, and the way models are used has now become more smarter. Instead of brute force, the industry is moving toward the precision. One of the clearest examples of this is distillation. A larger model acts as a teacher, and smaller models learn from its outputs. This allows the smaller model to inherit useful behavior without needing the same scale. This is already happening in real systems. Capabilities that once required large cloud models are now being distilled into smaller versions, and those smaller versions are run directly on phones and other devices in real time. This is how frontier intelligence spreads into everyday applications. Another shift is how problems are structured. Instead of asking one large language model to solve everything at once, systems break tasks into smaller steps. A system might first identify intent, then extract information, then verify it, and finally generate a response. The outcome looks the same, but the process is more efficient. In this setup, a smaller model can outperform a larger one because the problem is clearer and more structured. This shows that intelligence is not just about the size, it is also about how the work is organized. But there is an even bigger shift happening. In some modern AI systems, the entire model is not used at once. Instead, the model is split into many smaller parts, and for each request, the system only activates a few of them. This approach is called mixture of experts. Instead of one giant model doing everything, you have many smaller specialists, and the system chooses which ones to use, depending on the task that you give them. That means a model can have a massive total capacity, but only use a small fraction of it at any moment. So it behaves like a large model when it needed, but runs closer to a small model most of the time. This changes the meaning of the size completely, because now the question is not how big the model is, the question is how much of the model is actually active. Then there is a quantization, which reduces how much memory a model uses. Instead of storing the numbers with full precision, models can use lower precision formats, making them smaller and faster. In the past, this often reduced quality, but modern techniques have improved significantly. Today, models can be compressed while keeping most of their performance. And the shift goes even further, because now it's not just the model it's being optimized, it is the memory around it. When a model generates text, it keeps track of everything it has already processed, and that memory grows quickly, especially with long inputs. That is where something called turboquant comes in, which you may have heard in the recent news. That's basically revolutionized compressed using the memory for the AI models. The concept is simple. Instead of shrinking the model itself, TurboQuant compresses the memory used during the generation. That means the system can handle longer context, run faster, and use far less memory without changing the model itself. So the industry is not just shrinking the models, it is shrinking everything around them. Another important shift is happening during training. Instead of building large models first and compressing them later, researchers are starting to design models that are efficient from the beginning. These models are trained in ways that make them more stable and easier to compress. This means efficiency is no longer something you add later. It's part of the design from the start. At the same time, AI is becoming more system-oriented. Instead of relying on a single model, many applications use multiple models, and those models working together. A smaller model might generate a first draft, while a larger model verifies it. Other components handle retrieval, filtering, or memory. This kind of system is already being used to make larger models faster without reducing quality, which means performance is no longer defined by one model. It's defined by how well the system is designed. Large models are not going away. They still perform better on complex reasoning, open-ended tasks, and difficult problems. But they're no longer the only way to achieve a strong performance. What's changing is that many capabilities that once required very large models can now be delivered by smaller ones. That's not just a shift toward the small models. It's a shift toward making intelligence more practical, more efficient, more accessible, and easier to deploy. The first era of AI focused on making models as large as possible. The next era is focused on how small those capabilities can become while still feeling powerful. And based on what is happening now, we are still far from that limit. The future of AI will still include large systems, but the AI people actually use every day will be smaller and just as powerful where it matters. This is ML Guy, and together we will learn how the systems are working under the hood. Until the next video, good morning, good afternoon, and good evening. Bye.